Ladies and gentlemen, boys and girls, it's time to learn some math. So before we get started with that, we're going to do this nice little warm-up problem. So the first one that we're going to take a look at is just doing some division, which hopefully we see this special way that we can do that. After that, I'm going to ask if you guys can tell me yes or no, is quantity x minus 1 a factor of x cubed plus 7x minus 3. I'll give you a few minutes to do that, and then we'll come back to it. All right, so if we take a look at the first one where we're doing division, I need to first recognize that I'm dividing here by x plus 2, which is a linear binomial with a leading coefficient of 1. And because of that, I'm allowed to use synthetic division. So I can go and I can take this x plus 2 and I can set it equal to 0. And I can find its solution, which is negative 2, and that's going to be my synthetic divisor, okay? Then I can go and plug in all of the coefficients, because when I examine each one of the exponents, I see that it goes 3, 2, 1, none, so it's in standard form, so we should be good to go. So those coefficients are 1, 7, negative 11, and negative 20. Going through and doing synthetic division, I'm going to copy down that first term, then multiply negative 2 by 1 to get negative 2, add that to 7, and I get 5. Negative 2 times 5 gives me a negative 10. Well, negative 11 minus 10 is negative 21. Negative 2 times negative 21 is a positive 42. And when I have negative 20 and positive 42, I have a remainder here of 22. So basically what this is saying is that when you divide x cubed plus 7x squared minus 11x minus 20 by x plus 2, the result is 1x squared plus 5x minus 21, and then plus the remainder, which is 22 over x plus 2. Okay, so that's an example of one where we do the division and we have a remainder. Okay, because we have a remainder, we know that this polynomial isn't really divisible evenly by x plus 2. And because of that, we know that it's not a factor. Okay. So thinking about that, when we go and look at the second problem here, we're asking, is x minus 1 a factor of x cubed plus 7x minus 3? Well, in order for it to be a factor, it has to be divisible. So what I'm really asking is, can you do this division and interpret your result? So let's go ahead and do the division. So this would really be x cubed plus 7x minus 3, and then I would be dividing that by x minus 1. So using my divisor of x minus 1, I can come up with a synthetic divisor of positive 1. Okay. Then I could go and take my coefficients. My coefficient for x cubed is 1. My coefficient for x squared is 0. Okay, that's a 0 placeholder. My coefficient for x to the first is 7, and my constant is negative 3. So now I can start doing my synthetic division. So bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 7 plus 1 is 8. 1 times 8 is 8. And this gives me a remainder of 5. So is x minus 1 a factor? No, because it has a remainder. Now we'll get into the mathematical nitty-gritty of that later on in this unit when we start talking about the factor and the remainder theorem. But this is kind of a prerequisite for the information and the lesson that we're going to have today, which goes over the rational root theorem and also the fundamental theorem of algebra. Okay, so the rational root theorem is one of, in my opinion, the most interesting formulas because it was developed at a time before calculators. Okay, and if you think about what you would have to do to solve the kinds of problems that we're going to solve without a calculator, you will be very, very impressed with anybody that had to take an algebra class before Texas Instruments came in and gave everybody a wonderful graphing calculator that made everything so much simpler. But the rational root theorem is a very, very old theorem, but it's also very intriguing and interesting, even though it may seem a little daunting when you first look at it, okay? So what is the rational root theorem? The rational root theorem states that if a function, which we're just going to generically call f of x, equals, and this tends to intimidate a lot of folks, keep in mind, guys, this is literally just a generic way to write if f of x is a polynomial. A sub n just means the leading coefficient. X raised to the n is just the degree of that polynomial function, okay? So we have the first term, we got maybe some other terms, then we go down to a linear term, and a sub 0 is just a constant. So this is literally just a generic way to express any old polynomial function. So if a polynomial function, f of x, has integer coefficients, then every rational zero of the function has the form, and then it's really plus or minus here, p over q. P represents all the factors of a sub 0, and q is all the factors of a sub n. Well, what does that all actually mean? Well, it's just plus or minus factors of a sub 0 is my constant, okay? And then over a sub n, well, those are going to be factors of my leading coefficient. Okay, so basically what this is doing is this generates a list, and it says that if a polynomial exists with integer coefficients, then all of its rational zeros, okay, keep in mind rational means anything that can be written as a fraction, which includes all whole numbers, okay, will always be of the form plus or minus p over q. All right, now sometimes that's going to give you just a couple, other times that's going to give you a ton, okay? But before we move any further, I need to go through and do a little miniature review just to remind you guys of a couple of things, okay? When we say the word root, zero, or solution, they all mean the same thing. Root, zero, solution. Okay, those all mean the same thing. Okay, slightly different context. We're not going to get into the minutia in a high school algebra 2 class, but for our intents and purposes, all of those are the same thing. Those are also the same thing as what we call an x-intercept. Okay, a root, a zero, a solution, or an x-intercept. Okay, so if we have a nice pretty graph that's over here, and we go through and we draw something and it looks like this, okay, we're going to have several roots, zeros, solutions, okay? We're going to have one right there, one there, one there. So it's just where the graph is crossing the x-axis, okay? So it can cross the x-axis at rational numbers, like 1, -7, 2/3. It can have those kinds of x-intercepts. And if it has one of those, it'll come from this list of plus or minus p over q, okay? But this could also have x-intercepts at irrational numbers. If it's got something, a zero, a root, a solution, an x-intercept that is irrational, the rational root theorem is not going to tell you about it, okay? But it should be enough to get you to the point where you could find all the irrational zeros as well. Exciting times abound, all right? So what we're going to do is we're going to take a look at how to use the rational root theorem and then kind of combine that a little bit with what's called the fundamental theorem of algebra. The fundamental theorem of algebra isn't really a big thing that we need to go through and write down. It's just something you need to have in the back of your mind. But the fundamental theorem of algebra states that any polynomial of degree n can have up to n solutions. So a quadratic has a degree of 2. It could have up to 2 solutions. A cubic function has a degree of 3. It could have up to 3 solutions. Okay, a 10th degree polynomial is 10th degree, so it could have up to 10 solutions. Remembering that solutions are the same thing as roots, zeros, or x-intercepts. All right, so let's go see this puppy in action. So example 1 says, list the possible rational zeros. Okay, remember, we could go through and we could say zeros. We could also say roots. We could also say solutions. Okay, so all of those terms for the intents and purposes of this class right now are interchangeable. So list the possible rational zeros of f of x equals x cubed minus 4x squared minus 11x plus 30, and then find the zeros. We're just going to kind of dip our toe in the water for that right there. We'll get more to finding all the zeros on Friday, but we'll at least start exploring that concept. All right, so first off, if I'm going to go through and list all the possible rational zeros, that means that I need to come up with a list that is plus or minus p over q. The value of p and q are in the problem, okay? If we go back and we look at our definition, it says p is the factors of the constant, okay? So this is where we get p from. Q, okay, is the factors of our leading coefficient. Well, what's our leading coefficient? 1, okay? So plus or minus p over q is going to be equal to plus or minus all the factors of 30 over all the factors of 1. So the factors of 30 include 1 and 30, and then you've also got, what, 2 and 15, and then, what, 6 and 5? Okay, and I'm pretty sure that's all the factors of 30. Factors of 1, that's easy. It's just 1. Okay, but after we go and write it out like this seems like a weird list. This is just a shorthand way to write what I'm about to put. So this is really equal to plus or minus 1 over 1 is 1. The next largest number would be 2 over 1, which is 2. The next largest number would be 5. The next largest number would be 6 over 1, which is 6. The next largest number would be 15, okay? And then the next largest number after that would be 30, okay? Since all of those are divided by 1, basically you have a list here of plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 6, plus or minus 15, plus or minus 30. I don't want you to go and write out positive 1, negative 1, positive 2, negative 2, positive 5, negative 5, positive 6, negative 6. You see how that would take a really long time to write out and it doesn't serve an actual mathematical purpose? So this right here is what we're going to go and say is adequate for a list of possible rational zeros. You'll notice all of these are rational numbers. Okay, so this is our list that we got from plus or minus p over q, where p was just a list of all the factors of our constant, and q is a list of all the factors of our leading coefficient, which in this problem was easy because it was 1. So the next thing it says to do is find all of the zeros. Okay, well, earlier when we did the quadratics unit and you had to find all the zeros or the solutions of a quadratic, you had different ways to solve it. You could maybe factor it. You could maybe use the quadratic formula. You could take square roots. We don't have those kind of options for cubic functions, okay? Maybe I could factor it, but you'll see really quickly, factoring by grouping is not going to work. So I'm plumb out of ideas. But instead, I can remember something very, very important. Factoring is the same as dividing, okay? Big, big, big idea. Factoring is the same as dividing. So if I do division, then it's kind of like factoring. And since our go-to method for solving polynomials has been factoring, let's try and do that, okay? So we're not going to go through and find necessarily all of the zeros, but we'll at least find one, and I'll kind of, like I said, we're dipping our toe in for today. So in my list of numbers, the first number that I'm going to check is positive 1, okay? And I'm going to go and divide it. And because this is a solution, okay, or a potential root, then I can go through and use synthetic division. That's why we've been doing it so much for a review. So in my synthetic division little box boat thing, I've got 1, -4, -11, and 30, okay? So let's do synthetic division and see what we get. Copy down the 1. 1 times 1 is 1. -4 plus 1 is -3. 1 times -3 is -3. -11 and -3 is -14. 1 and -14 is -14. And I get a remainder of 16. If you have a remainder, it's not evenly divisible. If it's not evenly divisible, it's not a factor. So that one didn't work. So let's try the next one, -1. So same thing, 1, -4, -11, and 30. Copy down our first term, 1. -1 times 1 is -1. -4 plus -1 is -5. -1 times -5 is +5. -11 plus 5 is -6. -1 and -6 is +6. So that gives us a remainder of 36. If you do division and there you have a remainder, it's not evenly divisible. If it's not evenly divisible, it's not a factor. So that one didn't work. Next on my list is the number 2. Okay, 1, -4, -11, and 30 again. Okay, rinse and repeat. Take that first number, copy it down. 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. -11 minus 4 is -15. 2 times -15 is -30. And 30 minus 30 is 0. I got a remainder of 0. So guess what? I know that I could use 2 for synthetic division, which means that x minus 2, okay, because remember how we had to change the sign for doing this? So x minus 2 is a factor of x cubed minus 4x squared minus 11x plus 30. Okay, so we found one of the factors. And if this is one of the factors, isn't this part here also a factor? And what is that part? Isn't that 1x squared minus 2x minus 15? Okay, so is that a factorable or otherwise solvable quadratic that you could use to find all the other zeros? Interesting. We're not going to go fully into that just yet. Okay, we'll save some of that for tomorrow. But what we've done here is we've gone through and said, okay, I need to go through and try and solve this particular cubic function. I don't have a super special way that I've been able to do that. So maybe I can use what I've already learned how to do, which is factoring. Well, factoring is just really division, but I don't want to just randomly guess and check like what could I divide by. I want to have like a little bit more concrete, okay, thought process to that. So what I'm going to go through and do is use the rational root theorem. So I'm going to identify all the factors of my constant, divide them by all of the factors of my leading coefficient, and that's going to give me a list of things that I can check. Then just one at a time, I'm going to check them until I find a zero that works, a root, a solution, which I can then turn into a factor so that I can factor down this particular polynomial. All right, so let's take a look at one more. Example 2 says, list the possible rational zeros of f of x equals 15x to the fourth minus 68x cubed minus 7x squared plus 24x minus 4. Good golly. Okay, so if I'm going to go through and do this, I need to start at the same place. Okay, it's kind of like problem 1, list the possible rational zeros. Part 2, find one of them. Okay, or at least we'll find one for today. By the end of all of this stuff, you'll be finding all of them. So I know that I'm going to need to come up with a list of numbers that's defined by plus or minus p over q. That's going to equal plus or minus, this one is p, this one is q. So factors of 4, which I'm just going to do the little asterisk thing to remind me that it's factors of that number, over factors of 15. Okay, so that's going to be plus or minus. Factors of 4 are easy. 1, 2, 4. Factors of 15, also pretty easy. 1, 3, 5, and 15. So now that we've got all of our factors of p and q listed, it's time to go and write a list of all the possible rational zeros, roots, or solutions. So this is going to be equals, plus, or minus. And this next part is kind of a little weird going from this list. I realize it takes a minute to kind of get your head around. Just go with me. It'll be pretty easy once we go through and do it. So what I'm going to do first is I'm going to take just this first number that's in the numerator 1, and I'm going to put that as the numerator, and then I'm going to write it with a denominator of 1, denominator 3, denominator 5, denominator 15. So 1 over 1 is 1, 1 over 3 is 1/3, 1 over 5 is 1/5, and 1 over 15 is 1/15. Okay, so now I'm going to go to the second number and do the same thing. 2 over 1, 2 over 3, 2 over 5, 2 over 15. So 2 over 1 is 2, 2 over 3 is 2/3, 2 over 5 is 2/5, and 2 over 15 is, well, 2/15. Okay, then I'm also going to do the same thing for 4. Okay, but I'm running out of room, so I'm going to have to go and write it down here. So I have 4 over 1, which is 4, then 4 over 3, which is 4/3, then 4 over 5, which is 4/5, and then finally 4 over 15. Okay, so this is a list of all the possible rational roots. So how many is that? Remember the plus or minus. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So if you were really, really, really bad at guessing, you might have to go through and do synthetic division 24 times to confirm or deny that any one of these is a rational zero. Okay, I'm going to try and save you guys the trouble of going through and doing all of that, but I do want to show you just going through and doing a couple of these to see if we can find at least one rational zero. So let's just start with the positives, and let's just start with 1. Okay, we're randomly guessing. It doesn't really matter where we start, but I'm going to say let's start at 1. Okay, when I do my synthetic division little boat here, I'm going to have 15, and then negative 68, and then negative 7, and then 24, and then finally negative 4, right? So bring down my 15. 1 times 15 is 15. Negative 68 plus 15 is going to give us negative 53. 1 times negative 53 is negative 53. Negative 7 and negative 53 is going to give you negative 60. 1 and negative 60 is negative 60. Negative 60 and 24 is going to give you negative 36. Okay, and we should be able to tell 1 times negative 36 is negative 36 that we're going to get a remainder of negative 40. So is 1 a solution or a root or a zero of this quartic polynomial? No. Let's try another one. Let's try 1/3. Okay, I want to try 1/3 because I don't know if we've ever done one in class that involves a fraction, but it's actually not as scary as you probably think. Okay, remember, fractions are just other ways that we're writing division, especially when they have a numerator of 1. Okay, so I'm just going to go ahead and fill out my synthetic division box or boat. okay, and work our way through it. So we're going to copy down that 15. Now, 1/3 times 15 is really 15 divided by 3. Okay, 15 divided by 3 is 5. Negative 68 plus 5 gives us negative 63. 1/3 of negative 63 is really taking negative 63 and dividing it by 3, where we get negative 21. Negative 7 and negative 21 is negative 28. 1/3 times negative 28 is really negative 28 divided by 3, okay, which is negative 28/3. Ugh. That's not pretty, okay, but maybe I could go and use a calculator for this part. So if I did 24 minus, and then in parentheses, negative 28 divided by 3, I get 33 1/3, which written as a fraction is really 100/3. And then 1/3 of that is 100/9, and you can tell that's not 4. So you're going to end up with a non-remainder of 0 there. Okay, so and not all the time, but probably 95%. As soon as you start getting improper fractions inside of this, chances are 95% it's not going to be a rational solution, but you can keep working anyway. All right, so let's go through and let's try 1/5. Okay, maybe we'll have better luck with that one. So let's go through and set up our problem. So we've got 15, negative 68, negative 7, 24, and negative 4. Let's see what we get. Okay, just like before, when we were using 1/3, okay, it really means we're dividing by 3. Okay, so 1/5 is really dividing by 5. So if we copy down that first number and then divide it by 5, because 1/5 is like dividing it by 5. So 1/5 of 15 is 3. Negative 68 and 3 is negative 65. Okay, negative 65 divided by 5, which is the same thing as multiplying it by 1/5, gives you negative 13. Negative 7 plus negative 13 is negative 20. 1/5 of negative 20 is negative 4. 24 minus 4 is 20. And 1/5 of 20 is positive 4. So, whoa, check it out. We got ourselves a remainder of 0. So this means that something along the lines of x minus 1/5 is a factor, okay? And what's the other factor? Well, that's going to come from what's left over. What's left over is 15x to the third minus 65x squared minus 20x plus 20. Because if you multiply these two things together, what are you going to end up with? 15x to the fourth minus 68x cubed minus 7x squared plus 24x minus 4. Okay? So this is kind of us dipping our toe into solving by factoring. Because again, what are we doing? We're finding things that are divisible. If they're divisible, it means that they have to be factors of one another. So this is all really just big, fancy factoring, okay? So your homework for today, you've got a sheet where for each one of those, you have to go through and list all the possible rational zeros. When you're listing all the possible rational zeros, what I'm asking you to do is give me this list, okay? This plus or minus P over Q. Sometimes the list will be short. It may only have 3, 4, 5 things in it. Other times the list may be long. It may have dozens, all right? But then what I want you to do is I want you to try and find one of the possible rational zeros that is in fact an actual zero, okay? So 1/5 in this problem got promoted from it could be a 0 to it definitely is a 0.